So this is a tutorial on generative AI models. So generative models have emerged as a powerful tools capable of creating new and imaginative content by leveraging sophisticated algorithms and deep learning techniques. These models enable machines to generate realistic images, text, music, and even videos that mimic human creativity. Let us try to understand the ever growing and highly impacting world of AI generative models by understanding its definition, purpose, applications, and some concepts that drive its success. Generative AI models. AI generative models are designed to learn from various vast amount of data and generate new content that resembles the original data distribution. These models go beyond simple classification or prediction tasks aim to create new samples that exhibit artistic, intellectual, or other desirable qualities. Applications of generative AI models. AI generative models have found a wide range of applications in various fields. They facilitate image generation, text generation, music synthesis, video synthesis, and more. These models empower artists, designers, storytelling, and innovators to push the boundaries of creativity and open new possibilities for content creation. Key concepts in generative modeling. Generative modeling include latent space, training data, and generative tech architectures. Latent space is a compressed representation of data that captures its essential features. Training data serves as the foundation for learning and helping models understand the underlying patterns. Generative architecture, such as variational autoencoders, generative adversarial network that is GAN, autoregressive models, and flow-based models, are the building blocks that enable generative modeling. Types of AI generative models, a variational autoencoder. Now, this explanation of VAEs and their architecture. VAEs are generative models that utilize an encoder-decoder architecture to map input data into latent space and reconstruct it back to the original data domain. They balance reconstruction, accuracy of regularization to generate new samples that follow the learned data distribution. Training process and latent space representation. VAEs undergo a training process that involves optimizing the model's parameters to minimize reconstruction error and regularize the latent space distribution. The latent space representation allows for the generation of new and diverse samples by manipulating points within it. Use cases and examples of VAEs. VAE have applications in diverse areas, including image generation, anomaly detection, and data compression. They enable the generation of realistic images, art synthesis, and interactive exploration of latent spaces. GANs, the Generative Adversarial Network. Let's try to understand what is this and what are their components. The GAN consists of a generator network and a discriminator network and work together in an adversarial fashion. The generator aims to generate realistic samples, while the discriminator tries to distinguish between real and generated samples. Training process and adversarial learning. The training process involves an adversarial game where the generator aims to fool the discriminator and the discriminator tries to correctly classify samples. Through this competitive process, both networks improve their performance iteratively. Real world applications and breakthroughs with GANs. GANs have made significant contribution to image synthesis, enabling the creation of photorealistic images, style transfer, image imprinting. They have also been applied to text to image synthesis, video generation, realistic simulation for virtual environments. Regressive models. Overview of autoregressive models and their structure. Autoregressive models generate new samples by modeling the conditional probability of each data point based on the preceding context. They sequentially generate data, allowing for the generation of complex sequences. Training and inference process. Autoregressive models are trained to predict the next data point even with the previous context. During inference, they generate new samples by sampling from the learned conditional distribution. Use cases and examples of autoregression model. Autoregressive models are commonly used in text generation, language modeling, and music composition. They capture dependencies in sequences and produce coherent and contextually relevant outputs. Flow-based models, explanation of flow-based models and their characteristics. Flow-based models directly model the data distribution by defining an invertible transformation between the input and the output. They allow for both data generation and efficient density estimation. Normalizing flows and invertible transformation. Flow-based models utilize normalizing flows, a sequence of invertible transformation to model complex data distribution. These transformations allow for efficient sampling and computation of likelihood. Applications and advantages of flow-based models. Flow-based models have applications in image generation, density estimation, and anomaly detection. They offer advantages such as tractable likelihood evaluation, exact sampling, and flexible latent space modeling. Transformer based model. Explanation of transformer based model and its characteristics. Transformer based models are a type of deep learning architecture that has gained significant popularity and success in natural language processing tasks. Transformer based models are a type of deep learning architecture that has gained significant popularity and success in natural language processing tasks. Thank you.